Question number 26. A solid sphere of radius r and mass m is rolling without slipping on a horizontal surface with velocity of its center of mass v0. If it rolls without slipping up an inclined plane to a height h before it stops for a moment, then find h. Initially, the solid sphere possesses translational kinetic energy and rotational kinetic energy. So at the moment when it reaches to the height h, the only mechanical energy it possesses is potential energy. So I can apply the principle of conservation of mechanical energy as the rolling is pure rolling. So half m v0 square into 1 plus k square by r square must be equal to mg into h. So in the case of solid sphere, the value of k square by r square is 2 by 5. So if I substitute this data, then the value of h comes out to be 7 v0 square upon 10g. So option 4 is the correct answer. So the correct answer for question number 26 is option 4. Let's move to question number 27. In question number 27, a uniform solid cylinder of mass m and radius r is kept at rest on a rough horizontal surface. A horizontal force F is applied as shown in figure. If the cylinder rolls without slipping, then frictional force acting on cylinder is. So the point of application of force is at a distance of 3r by 4. So h is greater than r by 2 from the center of mass. So point of application of force is greater than r by 2 from the center of mass. So the direction of friction will act in the forward direction. So it is a result we know. So if I draw the free body diagram, so let the friction is acting in this direction. So this point is the instantaneous axis of rotation. So I can write torque equal to I alpha about this point. So F into this separation, so that is F into 3r by 4 plus r, that is 7r by 4 is equal to I. So I of solid cylinder about this point is 3 by 2 mr square into alpha. Since the cylinder is in the state of perfect rolling, so that is equal to acceleration of center of mass divided by r. So if I solve this, the value of AC comes out to be 7f by 6m. So if I write the translatory equation, capital F plus small f is equal to mass into acceleration, that is 7f by 6m. So on solving, the value of small f comes out to be f by 6 in forward direction. So option 3 is the correct answer. So the correct answer for question number 27 is option 3. Let's move to question number 28. In question number 28, the moment of inertia of a uniform semicircular ring of mass m and radius r about the axis perpendicular to the plane of the ring is I. Then we have to find out which of the statement is correct. So we know that in case of a uniform semicircular ring, the position of center of mass is at a distance of 2r by pi. So this is the position of center of mass, and the value of 2r by pi is nearly equal to 0.6 into r. So if ICM is the moment of inertia of this uniform semicircular ring about the center of mass, then moment of inertia about this point A or the moment of inertia about point O can be written as IA is equal to ICM plus m into d square. So the value of d is 0.4 into r square. Similarly, if I write the moment of inertia about point O and perpendicular to the plane of the semicircular ring, then it can be written as ICM plus m into 0.6 into r whole square. So I can say that IA is less than IO. So it is given in the question the value of IO is mr square and the value of IA is I. So I is less than mr square. So option 2 is the correct answer. So the correct answer for question number 28 is option 2. Let's move to question number 29. In question number 29, a plank of mass m is equal to m by 2 is placed symmetrically over two identical hollow uniform cylinders each of mass m, which are placed over a rough horizontal surface as shown in figure. A horizontal force F is applied on the plank. If there is no slipping anywhere, then the acceleration of plank is. So if we analyze the situation, then we can say that the uniform cylinders are in the state of pure rolling. So the velocity of this point is 0. So I can apply the instantaneous axis of rotation about this point or about this point. Since the uniform cylinders are identical in nature, so due to symmetry, we can overlap these two cylinders and make a system like this. These are two cylinders which are overlapping, and the plank is replaced by a block of mass m by 2. So F force is applied on this plank, and due to this force, the acceleration of plank is AP. So this is the instantaneous axis of rotation. So about this instantaneous axis of rotation, this system is in the state of pure rotation. So I am writing the torque equation about this. The torque of friction, normal and gravitational force becomes 0. So F into 2R is equal to I of system about this point. So this is equal to moment of inertia of the cylinder about this point is mr square plus mr square, that is 2mr square by parallaxis theorem, into 2 because of overlapping of the other cylinder, plus moment of inertia of this block about this point. So that is m by 2 into 2r whole square. So this is the moment of inertia into angular acceleration alpha. So angular acceleration alpha can be written as, if AP is the acceleration of the plank, then tangential acceleration of the topmost point of the cylinder is also AP. So alpha can be written as AP divided by 2R. So if I solve this, the value of AP, that is acceleration of plank, comes out to be 2F by 3M. So option 4 is the correct answer. So the correct answer for question number 29 is option 4. Let's move to question number 30. In question number 30, a uniform solid sphere of radius r is given velocity v0 and angular velocity omega as shown in figure on a rough horizontal surface. What should be minimum angular velocity so that sphere would return to initial position? In order the sphere should return to initial position, the anti-clockwise angular momentum must be greater than clockwise angular momentum about any point on the ground. So I can say that I into omega must be greater than or equal to m into v0 into r. Or I can say that 2 by 5 mr square into omega must be greater than or equal to m v0 into r. So on further solving, the value of omega is greater than or equal to 5 v0 upon 2r. So in order to calculate the minimum angular velocity, omega minimum must be equal to 5 v0 upon 2r. So option 3 is the correct answer. So the correct answer for question number 30 is option 3. By this, I wish you all the best for your preparation. Have a good luck. Thank you.